In this video, we're going to look at what is a machine learning model. We're going to look at a spam classifier. A classifier says what category something is. In this case, it's going to be spam or not spam. So that's a binary classification. I'm going to generate some data here. So we're going to generate 100 samples, and I'm going to keep the separation kind of close. So the blue points here are emails that are not spam, and the red points are spam. We have two features, email length on the x-axis, and then the number of keywords, so keywords that would lend themselves to being spam. And so you can see that the fewer spam keywords and the shorter emails tend to be not spam. And then on the other side, and I did this on purpose so you could draw a straight line through and separate the two classes. And we're going to look at how different models do that in terms of drawing this dividing line for classification. Now, the first model I want to show you is a perceptron. I'm going to hit auto train, and you can see here what the model is trying to do is figure out what are the right weights that I can use to draw this line that divides the two classes, that separates them. There's a coefficient or a weight value for each of our features. And so what you do is you end up with a math function. You multiply the weight times the value for the feature. And there's also a constant term called the bias, so you add that as well. Now you can see here we're through 180 epochs already, and we're not able to converge. Now we can look at this and draw, just draw a straight line like we would on paper. It's really easy, but this is a math model. It's having a hard time because the range of values for the length is much bigger. It goes up to 200, whereas the keywords only go up to 20. And so it's having a really difficult time kind of getting it to converge for that reason. So we're going to see where we land here. Okay, and so after 500 epochs, you can see we ended up with, not too bad. There's 17 errors, so we've still got some miscategorized points, but our accuracy is 96%, so not terrible, but, really the challenge here was the data. So here's our function that we end up with. So given this, our input x, so the coefficient for the email length is 0.223. You multiply that times the length value, then plus the other coefficient times the number of keywords, and then the bias and then minus 52. And if that value ends up being greater than 0, we're going to classify it as spam. Otherwise, we're going to say, okay, no, this is regular email, it's not spam. Now, in that training run, look at the fluctuation in the email length coefficient. It's just constantly bouncing up and down. And again, that's because we didn't scale our data. A lot of machine learning models really benefit from that. You can see the keyword count weight is much smoother. That has a smaller value. The bias is very smooth also. So I'm going to go ahead and scroll up here, and we're going to scale our data. Okay, now look at this. So now it's all within the range from basically like minus 1.75 to positive 1.75. So 0 is the average or mean value. And then when you scale it, minus 1 to 1, that's within one standard deviation. So 2/3 of the data points are going to fall between minus 1 and 1. But you're keeping still the relative aspects of the data. So instead of auto train, I'll just do a single step. And you can see here, after only a single epoch, we were able to converge, draw that perfect straight line that divides them. We have 100% accuracy, and really no errors. I think it had 6 errors when it first started. And then we got to a convergence. Now, how did we adjust the weights, the learning algorithm? You take the current value of the weight old. What was your error rate? So the target value minus predicted. Then you take a fraction of that, the learning rate. So you're going to multiply that times the input value to get a sense of the scale of it, but take a fraction of that. So basically, we're nudging the weight in the direction that we feel like we need to go. So here's the epochs. We only had the 1, and you can see where our values ended up. So, all right, so next I'm going to unscale the data, go back to the original scale. Now I want to show you a decision tree. So we're going to automatically train that, and look, the dividing line for a decision tree is very different, right? It's not just a straight line. It's basically like rectangles carved out. And these different shapes are controlled by the different nodes within a decision tree. The logic we're going to look at in just a second, but our tree, it goes to a depth of 4. And here's our actual tree. So each one is a logic. So you take for your data, if the number of keywords is less than 10.5, then you're going to keep going down the tree, this upper portion. If it's greater than 10.5, so if it's 11 keywords or more, then we already know it's going to be spam. You can see we're at a leaf node, class 1 is spam, okay? But for the upper part of this graph, what you would do is you just follow the logic at each step, And you keep going down. So again, we have a depth of 4 is the lowest you can go. And when you get to a leaf node, then you know, okay, that's how you decide what is the classification for my data, and you get a shape like this. So decision trees can be very powerful, especially when used in a random forest, which is kind of randomizing the different data, creating a bunch of decision trees, and then using the best, or the combination of those answers. And it also shows you the feature importance here. So the keyword count was slightly more important than the email length, which makes sense. Like I can see how that would be more important. All right, so let's do this. We'll reset our training, and let's scale the data again now. And now we'll do a support vector machine. So a support vector machine, we're using an RBF kernel with it. And so I wanted to show you can get a non-linear decision boundary. And support vectors what they do is try to find the best dividing line. So they figure out where's the line on either side, like that goes through the data points, and then find the average in the middle, so that for any unseen data, we feel really confident that we're going to categorize it correctly. So basically this is finding like the contours through our data to try to figure out what is that best possible line that we could draw. And because we're using a kernel, it can be nonlinear. So think about these different types of dividing lines, and that's kind of a way to consider how these different models work. And this geometric view of the data is really important in terms of understanding what the models are doing. We're going to talk more about that in a second. Okay, so we can think about our data in two different ways. We can think about it from the math, like the numbers or statistical view, and then we can also think of it from the geometric view. And here I've got some really simple data, just like these 4 data points. So 2 features, X and Y. So you got 1 and 2. And we can think of each of these as either a number, a point on our graph. So here's like, that's where point A is, or we can think of it as a vector. So a vector would be the line starting at the origin, 0, 0, and that has a magnitude or a length and a direction. So it's got an angle that it's pointing to in the geometric space. The geometric view is really important, as we just saw in the previous slides, because that allows us to look at where our data is relative to other data points. And from a statistics view, we could look at, what is the mean or average values of X and Y. We could look at the distribution. How common is it to see different values? If we're given a particular data point, is that a really rare data point, or is it kind of look like a lot of the other ones? So it's very helpful to understand these two different viewpoints. Now, we talked about the perceptron, which is a linear model. What is a linear model? You can only do the basic math operations: addition, subtraction, multiplication, division. You can't do like x squared or cubed. So when you have linear, you can add, all those coefficients, you still just end up with one linear model. So here we're showing if we add points A and point B, we basically just move the line from point B to start where A ends. And then we end up with that sum. So the red dashed line is what you end up with. And because these two vectors are pointed in roughly a similar direction, you can see how it really extends the length of the vector. So it amplifies that magnitude and is going mostly in the same direction. If I can change this here, and we can look at another data point. So let's compare or add points A and C. Those are almost exactly going in the same direction. So it really increases the magnitude almost exactly. And you can see if you have other ones, let's look at point D, you get something sort of kind of similar there. One of the most useful interpretations of the geometric view is similarity. So the distance between 2 points tells us a lot about how similar they are. If 2 emails have almost the same length and almost the same number of keywords, then there's very, very similar emails. And in the geometric view, 2 data points that are close together, we can think of as more similar. Now, what is distance? There's different ways we can do it. So L1 distance is Manhattan distance. That's this kind of orangish dashed line. And so that is, think about, I'm driving through the city streets. I can only drive on those, I can't like cut corners. I have to go to one intersection and then turn left or right. So that's what a Manhattan distance is. L2 is the red line, and that's just a straight line Euclidean distance that I would calculate using Pythagorean theorem. And then there's also cosine similarity. So if you have a lot of different dimensions, these L1 and L2 start to have a little less meaning. And so you just look at how closely are the two vectors pointed in the same direction. Are they pointed mostly in the same direction, or are they opposite directions, meaning they have opposite meaning, or are they orthogonal? Like if they're at a right angle, then one is really not related to the other. Okay, we're going to look at one more thing. We're going to look at this insurance use case. So this is kind of a more holistic example. I've got this insurance data that I got from Kaggle. It's got about 1,300 records, and it's just got these few attributes about a person. So age, gender, body mass index, BMI, number of children that they have, whether they're a smoker or not, the region of the country they live in, and then the target, which is what we're trying to predict. This is a regression problem, is what is their insurance charges for the year. So this is what we're going to try to do. And we can look at the basic statistics of this data set. So if you look at age, for example, the mean or average person in this training set data set is age 41 with a standard deviation of 13, meaning that about 2/3 of the people in this data set are going to be plus minus 13. So they're in ages from 28 to 54, for example. And you can see kind of the different percentiles. So it's also important to look at on the charges column. So on the low end, 4,700, that's probably a young person who barely goes to the doctor, maybe just a checkup. All the way up to the high end, 45,000. So unfortunately, that would be a person who is probably dealing with some kind of illness and spends a lot of time in the doctor's office or maybe even the hospital. So one of the first things you would do in a project like this, exploratory data analysis, get a feel for the data, what the distributions are. You can see this is the charges, our target value, or target attribute. The average is about 18,000. The median is a little less, 15,000. And you can see on this histogram that there's this cluster of people in this lower cost range, and then a smaller group that's in this really higher cost, probably dealing with more doctor or hospital visits. And this type of right skewed distribution would be kind of common in a field like insurance. Now, this correlation matrix is really interesting and important to look at. It plots or it charts every feature against every other feature. On the diagonal line, it's all going to be 1 because that's age against age, for example. But if you look at this column on the far right, that is the insurance charges. That's our target. And so if you have a positive number, that means as one goes up, so does the other. A negative, the opposite. So age, that's got a pretty decent correlation, meaning that as you get older, you tend to go to the doctor more. More things can happen. Sex or gender has kind of a small, so not small coefficient or relationship, not a lot. BMI, body mass index, not surprisingly, has a little bit more of an importance, right? Number of children, well, that's interesting. That's also got kind of an important factor. And then if we keep looking, so is the person a smoker or not? That is really high, a high correlation there, 0.93, meaning that if you are a smoker, your insurance costs go really significantly up. And then region of the country, not too much of a difference. So here we're plotting a couple of the attributes against our target value. So age, you can see, is pretty clear that as you get older, on average, your insurance costs, basically your medical bills and your visits to the doctor, go up. BMI is a little less conclusive, and we saw that because the correlation value is a little bit smaller, but it still does trend upward. As the body mass index gets higher, it does trend upward a little bit, which kind of intuitively makes sense. Now, if we look at this again, the smoker status, that is huge. This box plot shows kind of the range for if you're not a smoker, most of the values fall in this lower insurance range. And actually this dashed line to the upper dashed line, that's 25th percentile to 75th percentile. So where most of the values fall. But you can see on the right side, if you are a smoker, significantly higher cost. And you can see, wow, an additional cost looks like 23,000. So that is really significant. Try not to smoke if you don't need to, because that can make a big difference. Okay, so some of these we just showed the numeric values, but we have categorical values also. So gender on this, we're just showing male and female. Smoker is just yes, no, and then we have 4 regions of the country. Now you can't send in the string Northeast to a machine learning model. You have to convert this all to numbers because these are mathematical numbers. So for the binary choices, it's just a 0 or a 1, but in terms of region of the country, you're going to see it's 0, 1, 2, or 3. So all of those categorical, we always end up converting those to numbers because that's what our math model expects. Okay, so what we're doing here behind the scenes, I've implemented a linear regression model. So that's similar to what the perceptron is. We've got these 6 features and then the 1 target value. This is a regression problem. We're trying to predict a specific value. And when you train your model, you're going to split it. Generally speaking, 80-20 is common. 80% of the data you use for training and the rest you save for test. Why do we do that? Because if we trained on all of our data, we would have no idea how it performs on data that we haven't seen. And so that's why you do this split. So our test set is smaller. smaller. That's how we can measure how well we're doing. Now here's the actual coefficients that we ended up with in our linear regression model. And we saw that age was probably the most important factor. It's not the biggest number on here, but remember it's a coefficient. So you're multiplying that number by the age value. So like by the time you get to be 60, 70, 80, that really gets magnified. Whereas smoker is really just a 0 or a 1. So you can see, again, we saw what the impact of that was. But these are the coefficients that we actually end up with. And the intercept, or the bias, is this actually negative value. So the bias would be if you had a 0 for all of the features, but that's not possible because you have some number of children, you have some BMI, you are some gender that's designated in this study. So, it's never going to actually be negative, but you have to start somewhere. So that's where if we draw a line, remember it's a linear model, it's going to intercept the y-axis at that point. And you can see our model performed really well. This R-squared score, a value of 1 is perfect, so we're doing really well. And then training RMSE, root mean squared error. That means on average we were off by about $1,100. That may sound like a lot, but if you think about it, going all the way up, the values go all the way up to 45,000. So that's actually pretty good. So on training, that's what it was. When we tested, it was a little bit higher, which makes sense because that's where we're performing in the quote unquote real world. Another alternative error measure is mean absolute error. And so those numbers are a little bit smaller. So let's look now at why would you use mean squared error versus absolute error. On the red plot, that's mean squared error. So this plot is y equals x squared. And so you would take whatever the difference is, like could be under or over, squaring them always makes it positive, and then you're going to penalize more heavily the larger the error is, as opposed to mean absolute error. So if you have an error of 3 on MSE, it's going to be actually 9, versus MAE, the absolute error, it would just be 3. So a heavier penalty the farther off you are. And then this dashed line that you can see going through the data points, so that's the gradient. And so anywhere on this slope, or anywhere on this line, you can take that slope, and that's how I know what direction I need to move my weight in order to get it closer to what I think is the right number based on my training data. And so you would also take a fraction of that. That would be your learning rate. So that's how those weights actually get adjusted, and how we, iteratively try to get the model to converge on the best possible solution, which is the best parameter values that fit our training data. All right, we covered a lot of ground in this video, so I'm going to stop here. I will see you in the next video.